Good. So good morning, everyone. Thank you very much to be with us in this iCafe that is organized by the International Relations Office of the Hellenic Mediterranean University. It's a great pleasure to have all of you here, and especially Professor Stavroulakis from the Technical University of Crete. As usual, I'm going to provide a short introduction of the speaker. So Professor Stavroulakis, George Stavroulakis, is a professor at the Technical University of Crete, director of the Computational Mechanics and Optimization Laboratory. He holds a PhD from the Civil Engineering Department of the Aristotle University of Thessaloniki in Greece and a habilitation degree of the Technical University of Braunschweig in Germany. His research involves theoretical computational study applications and software development in the areas of computational mechanics, non-smooth mechanics, structural control and optimization, soft computing in mechanics, and structural analysis of monuments. His work has received more than 4,500 citations, and his H index is 35. Today's talk is entitled Neural Networks for Direct and Inverse Problems in Mechanics. And once again, Professor Stavroulakis, dear George, thank you very much for your contribution, and the floor is yours. Thank you.
Good morning. Thank you very much for the kind introduction. It's a pleasure to present some of our results in this group, and we hope, but now I need the permission to share my screen.
You have it. You have it.
Okay. Yes, yes. Wait a minute. Okay, I hope you can see my...
Yes, we can see your screen, but it's not in full mode.
Not in full mode. This is a problem.
Αν πάτε κάτω δεξιά, δίπλα στο 76%,
Ναι.
Δίπλα στο 76% θα δείτε ένα σύμβολο. Αριστερά του 76% θα δείτε ένα σύμβολο. Αν το πατήσετε αυτό, θα κάνει full screen. Αυτό ναι. Ναι.
Yeah. For some reason, the first picture is not appearing in this full screen. I'm sorry for this. I hope that everything will work further in this presentation. Well, the presentation deals with usage of neural networks, deep learning, artificial intelligence, and the exploitation of big data in the area of mechanics. We all know that neural networks are model-free estimators. The exploitation of big data in our context is related to the usage of data from experiments or from numerical simulation. As I will try to show you, these techniques have proven to be suitable for direct analysis, for example, a replacement of material constitutive law, or for inverse analysis, which is relevant to structural health monitoring. Of course, these are tools which are now very modern and very popular because everybody is talking for creation of digital twins for very complex systems. And neural networks is a basic component in this direction, in this development. Well, let me remind you the classical pictures of back-propagation neural networks. A lot of small, relatively simple.
Excuse me, Professor Stavroulakis, if you are changing slides, we cannot see this changing.
Oh.
Don't worry, these things happen.
Okay, I will try to...
Try to skip. I will suggest you try to skip the first slide and start, yes, start from there.
Okay.
Yeah, now we can see the rotation of the slides. Thank you.
Okay. Okay. a lot of relatively simple elements connecting the information, transforming the information through these lines from the one layer to another, collecting the information, the inputs, for example, x1, x2, xn, multiplied by suitable weights, w1, w2, etc. And then this information is post-processed at the node by means of some activation function there, which is usually a nonlinear function. And this thing is repeated again and again. The information is forwarded from the input layers to the output layers. And the main, of course, question is how to train, how to find all these components in order to approximate a relation, approximate a mapping by using suitable examples. This is the idea of back-propagation neural networks. Okay, from the simple neural networks known decades ago, we are moving to the more complicated deep learning neural networks. Simply speaking, from mappings between vectors, we are talking now for mappings between pixels and pixels, okay? And even more between dynamic objects. What is interesting in our application is also the ability to map techniques based on rules. For example, if we are talking about a fuzzy inference system, we can map on the neural network the rules of the system. In this way, we can deal with hybrid systems where the model-free estimator, which is the neural network, is supported by some rules, which can be written from an experienced user, from a scientist, from an engineer, etc. This is the ANFIS framework. I'm not going to talk about this in this talk, but we have used this for control purposes. Well, these are the various steps of setting a neural network, of calculating the synaptic weights, of correcting these synaptic weights by using examples. And this is an iterative procedure which can be done on a computer, can be realized by means of an electronic circuit, whatever. These are the details which are developed by people of developing these tools. We are simply users of these tools. Another issue I would like to mention here is the so-called big data analytics. Simply speaking, finding the nearest point in a big database. If we're doing a Google search, we give some words or some phrases, and then the machine tries to find the relevant web pages from a very big database it is in the computer. In our context, we are talking about finding the nearest record of an experimental measurement, for example, of an earthquake, of a wave propagating and reflected through a very complicated medium. This is the idea. I will show you some simple examples how we use this tool within a finite element program to approximate the constitutive relation, the material relation, by using a database of experiments. Well, let me start the talk, neural networks in mechanics for direct problems. We can estimate the solution from data using neural networks or other metamodels. First, we have to create data for training. Then we have to do the training of neural network, and then we have to see if we have succeeded to create a useful trained network. That means we can use this metamodel instead of the initial problem. For inverse problems, the way is pretty similar. Now we try to approximate directly the inverse mapping from the neural network. And then, in this sense, to solve directly the inverse problem. That means, again, we have to create a couple of examples, data, outputs to inputs. Now we use it in another way. We train the neural network and we use it to solve the usually complicated inverse problem. Well, if we're talking of more complicated problems, we can think of using neural networks to approximate more complicated associations, more complicated relations. For example, to correlate the microstructure with the homogenized material properties in a composite, or to take directly the picture from an electron microscope and then process it by using this technique and find the homogenized properties, mechanical properties, whatever. Or to identify cracks from photos and give a mechanical explanation how they have been created, how they have they can be taken into account in some calculations. And the last step, which is modern today, is to use directly the physics in order to train the networks. That means to work with physics-informed neural networks. Well, for data-driven, I already mentioned, we can think of replacement of the constitutive law with experimentally or numerically generated data. And nowadays, we have a lot of machines. We can collect a lot of experiments, a lot of data. And in this case, we can use either neural networks to create in a similar way a metamodel, constitutive relation in the form of a metamodel, or to use the machinery of big data analytics in place of the classical constitutive law. Well, for inverse problems, I'm going to show you some pictures reminding what is important here, wave propagation and reflection is a very important topic, because we can find hidden material properties or layers or defects. I have the impression, no. I have the impression that some slide is not in the order here, but in any case, the model problem is crack and defect identification. We can formulate it by solving the direct problem by using finite elements or boundary elements, and we can calculate the inverse problem by using optimization or neural networks. Well, why this is important? Structural health monitoring in buildings, engines, etc., and defects coming from the usage of these structures, earthquakes, impacts, etc. Well, the input-output relation. The input can be the service loads or test loads, for example, in ultrasound, or other sources you can imagine of having electromagnetic or thermal sources, and try to find the output, which is what you can measure: deformation, displacement, vibration, electric or thermal field. And then you have to compare this in order to solve the inverse problem. Let us take an example of a simple plate with a defect here, a loading and a support here, and let us try to correlate the deformation picture of the external boundary with the presence and the position and the size of a support. You may write down a relatively easy least square optimization problem, fitting problem, but you soon realize that numerically it's not easy to solve it if you start from the position of the crack which is far away from the real position. It is a nilpotent problem in the terms of mathematics, and requires a lot of experience in order to solve it numerically. If you have a crack that closes or an elastoplastic medium, then you may have nonlinear relations between inputs and outputs. That means the least square problem becomes non-convex and multiplicity of solutions may appear. I will show you some pictures later on reminding. This is an artistic interpretation how the neural network after training will give us by looking at the external deformation, the position, the presence, the position, the size, etc. of a defect. We have done it several years before by using boundary elements, and here are the comparisons between real and predicted positions of cracks. Here we have 81 9 by 9, 81 different solutions, and the predictions in one plot. There are publications where you can see the details. If we use classical optimization, we can succeed to do something. Here you see the iterations between first position of a crack and the final position. But if we have, for example, contact effects, etc., this technique stops due to local minima. And in this case, neural networks is a best solution, a best method to solve the problem. For three-dimensional problems, for complicated three-dimensional problems, and due to the fact that neural networks are solving the problem in practically zero time, it is a suitable technique for online structural health monitoring and other things. In dynamics, I will show you some pictures of wave propagation and reflection in a very simple two-dimensional problem, one-dimensional problem. Remind you that this wave propagation and reflection depends on hidden objects like cracks, etc. This is the so-called impact echo technique. These are three different classes of signals coming from a layer with a delamination behind this, with a delamination with contact, etc. And a neural network can be trained in order to resolve this problem and find the inverse analysis. In 2 dimensions, things become more complicated because, as we imagine, the wave propagates and is being reflected by external boundaries, by possible defects or cracks, etc. At the end of the day, if we are looking at a simple point, we have signals like this. Quite complicated to make any comparison. Here, what we have done is to choose suitable screenshots, time instances, in order to replace the dynamic signal with a static vector. And after that, we can correlate these static vectors for different signals with the defect, with the what we are looking at. Okay. This is the simplest solution we have done. I will show you more complicated approaches later on. Here are some pictures of the error between real and measured quantities for a plate with a defect in the middle. Absolute minimum is the position of the defect. But you see some parasitic local minima here. That means the y coordinate is more difficult to be found due to this non-convexity. And this depends on the wave you are sending. If I remember well, the Ricker's pulse, well-known people doing geophysics, is the most suitable, can identify this defect in a more suitable way. Well, our last application in this direction was the impact echo technique applied on the pile integrity. Impact echo, that means an impact at the head of the pile is propagating and reflected from the pile. This is a well-known technique for quality assessment of piles which are constructed on site with all difficulties to create them there with concrete and steel, etc. In our computer experiments, we considered piles with different diameters along the length, along the depth, and this created examples of piles with different defects. Again, we did the wave propagation and reflection analysis by means of this model, considering also the soil around this pile. You cannot avoid this. And then sample results are here, results of impact echo for two different defects. In this case, it was quite complicated to find suitable screenshots, and we did the dumbest, the simplest thing we could do. That means we took equidistant pictures, and then we used these pictures in order to correlate signals, dynamic signals from different effects. Any proposed to improve this approach will be warmly appreciated. Okay. Well, other examples of our work are shown here. Defect identification in a composite wing for a wind turbine by putting some sensors and correlating the response coming from during the operation of this component. We have some publications, older publications, and now the direct problem, the extension of the previous work in order to approximate the solution of direct problems. We're talking about extensive problems, expensive problems to be solved. That means nonlinear problems, complicated problems. It means the creation of the database with representative solutions is numerically or experimentally expensive. And then we're using the neural network in order to approximate the result of this problem, which I say again, it could be a very expensive dynamic finite element problem, which takes a lot of minutes or hours in the computer to be solved. Well, this simple problem is this truss, different materials, different cross sections, neural network to solve, to approximate the solution and the comparison of the solution, deformation pattern between loadings and deformation. Okay, I should have another picture which is not very effective here. If we put loadings and different cross sections again, this training could not be realized. It was not successful. That means even in this simple problem, there are mappings between material properties, between sizes of components, etc., which could be quite tough to be approximated by a relatively simple neural network. That was a recent diploma thesis, as you can imagine. Okay, that was a more complicated diploma thesis, springback prediction. In the area of metal forming, you put a piece of metal here between these two dies, and then after plastic deformation, this takes the final form like this. All components, for example, the doors of a car, etc., are produced in this way. The problem is that you have an elastic unloading. That means a springback. That means the shape changes after taking the part out of this press. And this is a big problem if you are using a novel material. If you have experience, you are in an industry and you do this for years with the same material and the same shape, then it's okay. you learn how to correct it and how to produce the right things. But if you are changing the material, you take a new alloy, for example, then people are trying to put more complicated things like elastoplastic analysis, influence of texture in the elastoplastic analysis results, and so on and so forth. But this is a very tough thing. That means it takes some hours in the computer to be solved for every new case, for every new shape, for every new loading case. We have stored a number of representative cases from the computer on a neural network in order to be able to do this prediction of the springback. Well, the next step, I think it is the last application, is the incorporation of data-driven and neural network techniques within the finite element program in order to do data-driven homogenization. What is the story here? If we have a composite material, and from this composite material we create a cool structure, then the microstructure affects the response. But you cannot take this microstructure into account because the model becomes very big. The idea is to have a simple model without this microstructure, and then to take into account the microstructure by doing numerical homogenization, by considering a representative volume element at every point, at every Gauss point, integration point, at every loading step, whatever. Whenever you are needing the stress-strain relation, the constitutive relation, you are doing a numerical experiment on this RV. And this gives you the result, and this result comes again back to the big problem, to the upper scale. This is a two-scale, a multiscale finite element analysis. This is known as a FEM-square multiscale homogenization. It is a very expensive task. The idea was to replace these solutions by using a database. And by using a database, which can be created separately before the calculation, by using finite elements, by using experiments, whatever. Well, this is the proposed, worked with, developed together with my student, Dr. Drosopoulos, who have been in Crete for a while and then did a career. He is now lecturer in United Kingdom. Well, the idea, as I told you, is to create a database with all quantities that are needed, stresses, strains, stiffnesses, and then this database interpolation provides the constitutive stress-strain response. You can use classical interpolation, you can use artificial neural networks in order to realize this interpolation. You can use even the big data analytics in order to move within and choose suitable examples from this database. Okay, this is an example here, a composite plate with a number of inclusions here. Instead of solving this, for every point, this is the RVE, this is represent the volume element. Instead of solving the plate by putting hundreds of inclusions, we solve the plate with a small number of finite elements, homogeneous finite elements, but the constitutive relation comes directly from this analysis with elastoplastic behavior, with delamination, debonding, with contact, whatever. Okay, here is the picture. Again, here is the replacement of the database by means of a neural network. And there are several technical ways to realize this with one neural network, with several neural networks, in order to have the inputs and the outputs, stresses, strains, constitutive, consistent stiffness matrix, etc. I'm not going to bother with these technical details. Just to give you an idea of how this thing works, I will show you two examples. One is a classical masonry structure with an elastoplastic relation for the mortar joints. And this is the RVE, bricks and mortar with different components, different mechanical properties. Here are several solutions of this RVE, stress-strain relations for several components of the stress and the strain. With blue is the database, that means the data we have created by using finite elements, and with red is the neural network approximation, quite effective in most of the cases. And then we use this finite element analysis at the upper level, at the level of a wall, for example, either connected with directly with the RVE and solving it again and again, or directly connected with the database. Of course, as you imagine, there is a big difference. That means this usage of neural networks makes this thing much more effective. This is a second example, an RV with a crack. Here are the solutions of the RVE, and here is the comparison between a plate with a lot of cracks, 100 cracks, and the plate where the influence of this micro crack is taken into account indirectly through this FEM-square tool. That means in this case, we can use a much simpler finite element model. That means a more effective solution. These are the results. Comparative, not in all cases 100% correct, but there are things which can be improved. We have recently published a book with Dr. Rosopoulos, including MATLAB codes for the realization of these things. So you are kindly invited to use these codes, and we can set up a cooperation on this basis. Well, the last topic I would like to show you in some details is our recent involvement in the exploitation of physics-informed neural networks. Well, together with Dr. Muradova, a co-worker of mine at the Technical University of Crete, in this case, instead of creating examples, you give directly the partial differential equation which governs the mechanical problem. And then, by choosing different positions in place or time, you create directly the example to be given to the network for learning. This is the idea. Okay, it seems that, okay, this is a bending problem. For every x and y coordinate, we have a differential equation, Kirchhoff elastic plate bending problem. The neural network is going to learn how to solve this differential equation. The idea is that the classical backpropagation neural network can be used for every position of the plate, x, y coordinate, these are the inputs, to approximate the plate deflection. But then, using, for example, automatic differentiation, the same neural network can give us an approximation of derivatives, partial derivatives of the deflection. That means we have everything we need to set up the partial differential equation that governs the plate bending problem. And then, for every choice of for example, synaptic weights, we can see if at a given point, the chosen neural network can fulfill the differential equation. If not, we have an error, and this error can be used for further training. This is the idea. In some way, the boundary conditions are given for points that are lying at the boundary. For example, here you see a number of points in the interior and in the boundary are used in order to train the network, and the training is based on an error composed of an error of the differential equation. This is the second part here, and an error based on the boundary relations. This is the first part here. This is quite effective. Here you see a cross section of the plate, the deflection coming from the exact solution and the neural network. This is, in some sense, a development of the mathematicians know it. It is a collocation type method to solve the mechanical problem behind this. Okay, just to say a few words, but in the conclusions maybe. Okay, now we are coming to the conclusions at the end of the talk. I would like to give some thoughts how we can use data-driven computational mechanics, how we can work further in the direction of the topics I have mentioned. Well, the constitutive relation is a relation between stresses and strains, or strains and stresses, okay? We can use a database, this is the normal way, measurements of stresses and strains, but the classical way is to choose, in addition to this, a model, a mechanical model, mathematical model, classical, linear or nonlinear elasticity, plasticity, whatever, viscoplasticity. And then you try to adjust the model to the measurements. The modern idea is to take directly the measurements and try to use big data techniques in order to put the measurements directly in the mechanical numerical model. Well, within computational mechanics, we use, for example, projections to the database in the place of the classical constitutive law. How this works? Let us say that we have a stress-strain relation. We have these points here. These are the measured examples. These are the experiments we have done. We can create a Delanoë triangulation here in the space, and we see that every point lying in this area, for example, is nearest to this experiment. If within an iterative procedure you are here, you have to choose this experiment, and this is the representative experiment, the most suitable experiment for the database you can use further for your computations. This is the idea. Well, let me. There are extensions to this for nonlinear problems, for dynamic problems, okay? And if we're lucky enough and do this deep learning with pixels, we can think of more complicated things relating measurements and microstructures and response, all fusion, let us say, of information to support complicated calculations. Well, further work can be done also in the area of PINs, physics-informed neural networks, for problems with uncertainty, especially for inverse problems, because you have seen there's a comparison between predictions and real data. You can put side by side predictions of a model and measurements at specific points, and then you have a unique framework in order to solve inverse and direct problems by using neural networks. Of course, these things are quick. That means you can solve, and this is the attempt nowadays to solve complicated fluid structure interaction problems by means of pins in order to give to an airplane whatever real-time information of changing weather conditions, etc. Or for embedded systems, how to store or use multi-physics computations combined with control and all these things we want to solve and in real time. Well, we have published a lot of papers and results. You can find it in the web page of the Institute. And we are reading things published by other people. Here's a collection in the direction of deep learning and data-driven computational mechanics, which is a hot topic nowadays. Okay, thank you very much. You are kindly invited to visit the webpage of our institute. We're always improving it. It's not complete, but as you imagine, you can find something if you're interested in this direction there. Thank you very much.
Thank you very much, Professor Stavroulakis, dear George, for this very nice presentation. For me, it was something new since I'm coming from a different discipline. I will provide now the floor to the audience. In case you have some questions, you can type your questions or you can express your question by switching on your microphone. First of all, of course, you should use the virtual hand in order to be able to identify who is asking. We have already the first question. I have some questions. So the first question comes from Professor Fuskitakis. Please introduce yourself to the speaker in order to know with whom he is talking. Thank you. George, the floor is yours.
Thank you, Kostas. Good morning, Professor Stavroulakis. Thank you very much for being with us. Probably you remember me. I'm a mechanical engineer coming from the Department of Electronic Engineering from the Hellenic Mediterranean University. I'm a little bit familiar with structural health monitoring and more specifically with stochastic techniques from random vibrations. I would like to know if your techniques provide the answer to all three questions in case of faults. Do we have a fault? Do we know where the fault is, the fault location, or even the magnitude of the fault? This is the triple question we have to answer when we are talking about fault detection. If we have a fault, if we can locate the fault, and it's also very important to answer about the magnitude of the fault. Thank you very much.
Yes, thank you very much. It depends on the way you are preparing the data and you are doing the learning. You can prepare a lot of data with or without faults, and then you can have a binary, for example, variable in order to show the existence or not of fault. In this way, we can, in some sense, work with the first question, if there is a fault or not. We have worked on the definition, on the finding of the location and the magnitude by solving what I have shown to you, cracks and holes, up to 3 or 4 different defects, and we can identify their position and their size within the parameterization we have chosen. In this framework, we have, in some sense, the flexibility to find if there are, for example, 2 or 3 cracks in a machine component by using a bigger number of possible cracks. And then if some quantities goes to the 0, then we have an indication that there is nothing to be found there. This is a solution we have given to this question, finding the location and the magnitude, the same problem, and the existence or not, either by using binary quantities or by using classical parameters, and then if within the solution we find these parameters to be equal to 0, then we stop and say there is nothing to be found. But of course, there are a lot of things which can be done in the future in this direction. Thank you.
Costas, may I ask something else?
Yeah, of course, go ahead. And
thank you. I would also like to know if such models like neural networks, if they are capable of providing some information regarding the system itself. I mean, in case someone uses transfer function models, there is a possibility to associate the model parameters with the system parameters like damping ratios, natural frequency, and so on. Meaning that you have a model representation of your system, but at the same time, you have a relation with the actual system characteristics. Do neural networks provide this capability? We know that they are very powerful black boxes, but they can, let me say that, they can be blamed that they do not offer an insight for the system itself. It is a black box. If it works, it's okay. If it doesn't work, then you can do anything more. Thank you.
Yes, thank you very much. This is a big question, how to extract knowledge from the black box. I don't think there is a way you can do that in a simple manner, okay? We cannot do that for the applications I have shown you, except from the hybrid fuzzy inference and neural network model. In this case, you have a framework with rules, that means some model, and then the neural network simply changes some parameters in order to make this inference tool working better or according to the available data. In this case, you can say that you have a model, not the physical model of the system, but the model embedded on the neural network, and this model is extended and modified in order to fit with the measurements. Maybe the transfer function could be embedded on the neural network in a similar way, and then you have, instead of the weights, for example, of the neural network, you have the damping ratio or the mass or the stiffness components, but I don't know of any attempt in this direction. This is a very interesting topic. And I think also people from informatics will say that it's a very difficult problem to extract knowledge from. I have tried the same problem, inverse problem, crack identification, instead of using neural networks, to use fuzzy inference directly. And what came out for this simple plate example with one crack, I got something like 30, 40 rules to correlate measurements from specific points with the existence, position, size of the crack. That means nothing I could understand. Thank you.
Thank you very much. Thank you, Kostas. Thank you, Mr. Stavroulakis.
Thank you, George, for the question, and Professor Stavroulakis for the replies. We have a question from Ioannis Smirnakis, Professor Smirnakis, from, I think this is from Mechanical Engineering Department in Hellenic Mediterranean University. Yannis, the floor is yours.
Hello.
The camera is off.
Can you hear me?
Yeah, we can hear you very clear.
Okay. Thank you very much, Professor Stavroulakis. I am Yannis Smirnakis from LMEPA. I'm a mathematician, basically. At some stage, I mean, I would like to ask you a little bit more about the kind of neural networks that you are using. At some stage at the beginning of the talk, you mentioned the imposition of rules on some layer.
I think, Ioannis, can you please repeat your question because there are interruptions?
Okay, can you hear me now?
Yes.
Okay, the question is basically the rules that you impose on the neural network. Is it something more than the local connectivity, or you have some way of imposing restrictions on layer-to-layer transformation?
No, this is classical backpropagation neural network. The picture I have shown you, ANFIS, mapping of ANFIS, it's again modified to be written within the backpropagation machinery. Nothing special, nothing complicated.
Let me give you an example. I mean, in the differential equation example that you mentioned about deformation, one would like to impose locality because the differential operators are local. So on layer-to-layer transition, you would like to have only local connectivity. Is this something you impose, or you connect every node to every node?
Yes, thank you. First of all, you are talking about local connectivity between the position, let us say, in the plate and the result of the differential equation. This is not related with the connectivity within the network. That means hidden layers is our machinery to approximate the solution of the differential equation. I don't think you can impose locality by using this nodes. If I'm allowed to write, maybe you could think of adding additional nodes here in order to see the vicinity of the position you are looking on the plate, and then try to correlate the solution from all this geometrical information by using this or a more complicated neural network. This could be, for example, a proposal to solve a problem with non-local mechanical theories, second-order theories. This could be, I haven't seen this till now, but I don't think directly that the connectivity within the hidden layers has nothing to do with the connectivity with the vicinity of the points.
Sure. One more comment I would like to make is that there is now a neural net which is in the form of autoencoders, which allows to study the structure of the data. The idea behind it is that you use some input and then you reproduce some input, but somewhere in the middle, you use a reduced node layer. So somehow the system is enforced to encode the input data to a lower dimensional space, and then from this lower dimensional space to reproduce the whole data. So you get features of the data out of this. Maybe this could be used to learn some structure of the input data. Okay, thank you very much.
I will try. It doesn't move. I will try to show you the picture of the constitutive relation and the approximation of the neural network in order to give you a reply for this. Wait a minute. Okay, let us think of I hope you can see this slide with verification of stress strain training.
Yes, we can see.
Okay.
Yes.
You have here to correlate a tensor. That means 9 or more quantities of stresses with another tensor of strains. You can follow several ways. The simplest way is to correlate the tensor of strains with every single quantity of the stress tensor. That means sigma in the x direction, sigma in the y direction, sigma in xy direction, etc. This is the simplest you can do. The second is to correlate tensors with tensors without giving any further information. This is what we have done in this paper. But you can put more information there, that the constitutive relation is a relation of a material with a certain symmetry. That means the tensors are symmetric. Or, for example, we have an elastoplastic relation. And this is what you are, I think, is behind your question. To put this information inside. There are attempts to do that, even in the classical neural networks. And then, of course, in deep learning, in these autoencoders, you could possibly put this information within these layers as a filter, additional filter, or you can hope to find it automatically by using the big data. Thank you.
Thank you very much.
Thank you, Ioannis and Professor Stavroulakis, Ioannis for the question and Professor Stavroulakis for the replies. Do we have any other question from the audience or through the chat or through the mic? So I would like to ask you the last question. I'm not familiar with what are you doing. I'm following, other colleagues' work. So the main idea behind, the neural networks is you are providing some inputs, then your system interacts and you generate the outputs. Am I right?
Yes.
So you demonstrate these applications regarding the studies of materials, etc. What about if we try to apply this kind of approach, for example, for therapeutic reasons or for learning reasons? So to operate in the human brains and, to provide some input, some information, and then, to change the behavior of the human. For example, they are using, in order to not be misunderstood. For example, they are using music, right now, in order to try to make drug addicts to avoid these habits and, this use of, and the use of drugs, using music. So they train, through the music, the psychology of the humans is trained in order to avoid this habit. So how can we use the combination of bioelectronics, brain electronics, in order to train our system to avoid, for example, bad habits like use of drugs?
Oh, this is a very difficult question. First of all, we're trying to copy the function of the brain, of the nervous system. And what we are doing, of course, is very simple, very naive in comparison with the reality, with the prototype. I know that there are a lot of applications in the biomechanics area, and this is a very important area. Even what I have shown you, to find from external stresses hidden cracks or defects, could be used, for example, in the context of the mammography or CRography or other medical examinations, in order to find from what fingers are sensing the existence of a tumor, whatever. This could be a very interesting, is an application which is being developed from people. But the other way around, to use a neural network in order to retrain a human being, in order to avoid or to follow a pattern of behavior, could be possible, but I don't have an idea how to do that.
Okay. So, all right. So, I mean, I'm satisfied with the answer. I was thinking not only the medicine, but also what we are doing in the universities now that we are moving to personalized education from the massive education that we provided, 400 years ago, which means that such systems you can, for example, using the appropriate pedagogies, you can train somehow the students how to learn, and using the data from the exams or any assessments that we are doing to change our pedagogies, and then try to map, the learning experience of our students, which will be very beneficial, for the universities and go on. Or the automation, for example, of procedures in the lab in order to not consume so many consumables and the cost, and this will contribute to the cost effectiveness of anything that we are doing. I mean,
I have a quick reply.
Okay,
my student, Dr. Bekas, is working with people from the West Attica University to evaluate the learning output of online courses related to CAD, mechanical engineering, and how we react. I haven't studied the results.
Is he among the audience, or
I don't think so. I don't think so.
Can you send me his email in order to contact him?
Of course.
Okay. And we have another question now, I'm sorry, from our colleague Haralabos Koutroulis. Haralabos, the floor is yours. Thank you.
Thank you, Mr. Petridis. I have no any question, just to welcome Professor Stavroulakis, an old friend from our university years. Welcome, Yorgos, to our university. Thank you.
Thank you very much, Lapis.
It seems that Professor Stavroulakis has a lot of friends, because also Professor Valianatos also mentioned this yesterday to me, that my friend Professor Stavroulakis will be the today speaker.
George is not only a friend, but it's a collaborator. He's a research director in the Institute of Solid Earth Physics in our in the university. He's a member of a distinguished member of the institute, I can say.
Thank you.
Okay, so if this is the case, I don't know if our vice rector, I can see Nektarios Papadogiannis is here, would like to say something. It's time to close, Nektarios.
Just I say that we collaborate very much with Yorgos Stavroulakis in different projects. We have some common publications, and there is also a PhD coming out from our work few years ago, Kaselouris Vangelis.
Excellent.
Thanks for the collaboration and for the attitude, and for the help in our actions in the institute and in our university.
Excellent.
Thank you. I'm looking forward to continue the collaboration.
Excellent. Okay.
Very important for us also.
So it's time to close the session. We would like to thank you again, Professor Stavroulakis, for the input, for the contribution, for this very nice talk. We are going to continue next week with a speaker from Sweden, Professor Ellen Moons, that she's going to speak about the work that they are doing using X-rays in order to study the performance of perovskite solar cells and in general energy harvesting devices. So until next time, I would like to thank you. The whole talk will be uploaded on the YouTube channel of the International Relations Office of the Hellenic Mediterranean University. Over there, you can view also the 46 talks that they have happened through this action. We would like to thank all of you, and the speaker particularly, but all of you, because without you, nothing will be realized. Thank you, and see you next Friday. Bye.
Γεια σας Γιώργο, ευχαριστούμε.
Ευχαριστούμε Γιώργο.
Γεια σας.